So here we're going to do another in-class problem that we'll probably talk about in Zoom, but here's a quick refresher of what we went over. So in class on Tuesday, we discussed the root locus of a system where we had our open loop system was equal to G O of S 1 over S plus 2. So we had a pole at 0 and a pole at -2, and our root locus looked something like this, where we could reach any point on that root locus, but if we want to reach somewhere else, that wouldn't be possible. And we gave the example of saying that we wanted to go to -2 plus 2i as a desired pole location. So this could be based off of the fact that we wanted a certain natural frequency, we wanted a certain damping constant. We'll use those requirements from our design needs in order to choose our pole locations. And then when we have a desired pole location, we can see, one, is it on the root locus? So we can check if it's on the root locus by looking at the angles that go from our open loop pole locations to our desired closed loop pole location. So we have theta 1 and theta 2. And theta 1 was equal to 135 degrees, theta 2 was equal to 90 degrees, and we can just do that from trigonometry, knowing that we have a triangle length of 2. And we wanted to have our system, if it's on the root locus, our angle GO of S, and in this case S would be equal to 2 plus 2i, was equal to negative theta 1 minus theta 2, so negative 90, negative 135 gives us negative 225, which means that the position is not on the root locus, because if we set 180 2n plus 1 equal to negative 225, we get that n is equal to negative 1.125. That is not an integer. Since it's not an integer, it means it will not work. That point is not on the root locus. So what we can do is we can place a 0 in order to cause our angle GO of S to be on the root locus. So we can say our angle GO of S, negative 2 plus 2i, which just tells us the point that we're looking for, would be equal to some angle from our 0 location minus 225, because those are where the poles are, we're not changing those, and that this could be equal to, and we'll say negative 180, because we're very close to negative 180. We can add something to get us to negative 180, so that's going to be where we're striving to be. So we want our n to be equal to negative 1, so it'll be an integer. And this happens if we had a 0 at negative 4. If our 0 is at negative 4, we now have that this has a 45-degree angle, and because it has a 45-degree angle, it will now be on the root locus. So we can say that we are going to have a controller that will now be a proportional derivative controller. So if we want to visualize it, we're going to say that we have some KD, so our derivative controller, plus a KP, which will be our proportional controller. This will go to our open loop system, and we'll have a feedback control. And for this, we would have that that we would need to find both the value of our KD and our KP. We've now added a derivative. We've added a 0. And instead of writing our controller as KD, S plus KP, we're going to write it in terms of KD, S minus our 0. So in this example, we have a 0 at negative 4, so we can say that our controller is going to be KD, S plus 4, because that'd be S minus negative 4. And we can move this 0 that we've placed into our open loop system, because if we combine this part with our open loop system, we can now use root locus to find the value of KD. So we're going to be able to visualize that as KD S minus Z GO of S, and then we can now visualize KD as a proportional controller that we are doing on the system. And so here I'll just put in the values for the system we've been working with. So we'll have S plus 4 because we've added a 0 at negative Z at negative 4. And we will have S plus 2 on the bottom. And this is our feedback loop, and now we can use our angle criterion to double check that the point is on the root locus. But if we do that angle criterion, that would just be the math we just did, where we have that our angle GO of S equal to negative 2 plus 2i, because it's the point that we're looking at. That would be equal to negative 180. We just did that work. We don't need to do it again. So now what we want to do is we want to use our magnitude criterion to find what KD should be. So if we use our magnitude criterion tells us that the magnitude of GO of S is going to be equal to, if GO of S is in the A times the length of 0 vectors, or the product of the length of the 0 vectors. Running out of room there, divided by the product of our pole vectors. And in this case, we had that GO of S is equal to S plus 4 over S times S plus 2, so A is equal to 1 since there's nothing multiplied by that. And if we draw out our poles and our zeros, so we had a pole at S is equal to negative 2, S is equal to 0, and we have a 0 at negative 4. And our desired pole location was at negative 2 plus 2i. So just like with our angle criterion, we have those vectors drawn out, and we can refer to this to L1, L2, and L3. I'll call it L3. So we can say that the magnitude of GO of S is equal to 1, since A is 1, and L3 is a 0 vector, so we'll put that on top. And we had green for these, so we have L1 times L2 are our pole vectors, so we'll put them on bottom. And we have that L1 and L3 should be the same length because they both have legs of 2 and 2. And so they should be 2 root 2 for their length, but we don't even need to know that because we can see that they're the same. So GO of S is just going to be determined by the length of L2, which is just 2. So it'll be equal to 1/2. Since we have 1 plus k GO of S is equal to 0, that means that k is going to be equal to 1 over the magnitude of GO of S, which in this example is going to be 2. And you can use MATLAB and use a root locus of S plus 4 over S plus 2. And so we could do root locus of the transfer function, and that would be 1, 4, and 1, 2, 0. And we got to close that parentheses or MATLAB will yell at us. And then you can just use your scoping tool to find the point with the data cursor. So if you want to see me do that, I hopefully did that correctly in Zoom today, which for me is tomorrow, and for you maybe yesterday. Days are all very strange online. But you could see the MATLAB portion there. This is just a little recap of what happened with the math. I hope this helps a little bit with PD control. We're going to go through another example problem on Tuesday, April 14th. So if you want to download the Simulink file, try to work with it on MATLAB ahead of time, you can do so, and we will do that in class together. Hope you have a good weekend.